Hi and welcome to this video from the Year 2 part of the Statistics course, and we're looking at some content from the Data Presentation section of the course. And in this video we're going to be having a look at something called the Product Moment Correlation Coefficient, and then also looking at how we can calculate the equation of a regression line from a scatter graph. You should have done some work on scatter graphs in Year 1, so what we're going to do is just extend that a little bit further in Year 2. So here we go. Let's say we've got results from a chemistry experiment. So what we've got is the yield of the chemical reaction at different temperatures. And clearly you can see there, as we increase the temperature at which the reaction occurs, we're going to get more of a yield. So initially, from looking at that, we can make, that's what's essentially a subjective judgment. So we can say that looks like it's got a strong positive correlation, because we can see that, you know, you could draw a line of best fit through here and most of the points would be quite close to the line. So we might say, let's say it would be a strong positive correlation. But the idea of strong is quite subjective. So what we're going to do is try and quantify what we mean by strong correlation or weak correlation. We're going to try and put a value to those judgments, and that is what the Product Moment Correlation Coefficient, or pmcc, allows us to do. So here we go. What we're going to do, I'm going to take you through where the pmcc comes from, but essentially it's going to be tested more on your interpretation of it rather than the actual calculation from it, because as you'll see in a minute, you're going to be able to get this straight off the calculator. But I think it's always a good idea to know a little bit of the background behind these things. So what I'm going to do is, for each data point I've got in the graph there, we're going to calculate how far away from the mean it is. So what we've got is some point there. I'm going to pick that one there, and we do a calculation. We realise that we basically average the x values and we get x bar, average the y values, we get y bar, so we get this point here that is our average point. So if we calculate how far away for each point our x values are, so for our point that we've selected, that distance there is going to be the difference between the x value of our point and the x value of our mean point. And similarly, the vertical distance is going to be y minus y bar. So we've got those two values for each data point. We're going to do that for all the data points that are on our graph. And then we're going to calculate the product for each individual point, which is just those two brackets multiplied together. Now, here comes the cunning bit. Our graph is split into 4 quadrants based around that mean point. And so what we've got is, if we've got a point in quadrant number 1 up here, both x minus x bar and y minus y bar are both positive, so the product will be positive. But if, for example, I had a point, and I haven't got my down on this one, down here, then I would find that x minus x bar would be positive, but y minus y bar, because the y value is below the average y value, what we've got is a negative for that particular distance. So we've got a positive times a negative, which is a negative. So you can see here in this n column here, this is the key one. For quadrants 1 and 3, we're going to get a positive product, but for quadrants 2 and 4, we're going to get negative products. Okay, so what does all that mean? Well, if we add all of those things up, if we've got the points, more points in quadrants 1 and 3, they're going to be the positives, then we've got 2 and 4 the negatives, then the sum of all those things will be greater than 0, because we've got more positives than negatives, and that's what's giving us a positive correlation. And the reverse occurs if you've got more points in 2 and 4 than you have in 1 and 3. You'll end up with that summation being a negative, which is a negative correlation. So straight away we're starting to see this idea of positive versus negative correlation. And then the final part to that one is, if they're reasonably equally shared out amongst all 4 quadrants, then the positives and the negatives are going to kind of cancel each other out, and you're going to get a value close to 0, which means you've got little or no correlation. Now, a couple of other extra bits and pieces that we've got to think about. The first of these is that we've got to adjust for the size of the data set, and the second is we've got to adjust for the size of the values. Because obviously, if you've got a very, very large data set, you've got more values, this summation here is going to be much, much bigger. So we've got to account for that, and that's very easily done. We just essentially average them, and so we're just dividing by n. To take into account the size of the data values, if you have a look at our graph here, we've got a range of values here going from 100 to 170. So our x minus x bar values are going to be considerably bigger than our y minus y bar values, because our range of values here is only going from 1.6 to 3.6. So we've got to adjust for the relative size of those, and to do that, what we do is we divide by the product of the standard deviations of those two things, that standard deviation being measuring how spread out things are. Now, this is where it's starting to get a little bit complex, and you might be thinking, oh my god, where are we going with this? Well, you'll see in a second where we're going. We're getting the product moment correlation coefficient, and we usually refer to that as R. And it's that thing there, which looks absolutely terrifying, but in actual fact is reasonably straightforward to do. But as it turns out, you don't need to have to do it yourself. You're not going to be asked to do it manually because you'll be able to just get the calculator to spit this value out for you. So essentially the last slide was just about where the pmcc comes from, but as far as you're concerned, it's a number that's going to pop up on your calculator screen, and you're just going to need to be able to make sure that you understand how to interpret it. So here we go. Coming back to our chemistry experiment, what we're going to do is grab your calculators, put those values into your calculator as you would normally, and hopefully by now you should be familiar with getting all those different values from your data sets. And so what happens is you end up with a value of R, which in this particular case is 0.953, which indicates a very strong positive correlation. Now, let's go a little bit further with that. I've said that's a strong positive correlation. How do we know it's a strong positive correlation? Well, the first thing is the pmcc is always going to have a value between 1 and -1. It's never going to go above 1, never going to go below -1. And the value of 1 would be a perfect positive correlation, which means all the points are exactly on the line of best fit. If you get something looking a little bit like that, from round about 0.7 upwards, we're saying, okay, from that value onwards, we're getting a strong positive correlation. So that would be between 0.7 and 1. If we're getting a value between round about 0.4 and 0.7, we'll say, yeah, there is a positive correlation, but it's quite a weak correlation. And a value that's below 0.4, and I've put mod R below 0.4, so that means between -0.4 and positive 0.4, i.e. close to 0. Basically, we've got little or no correlation at all. And the same thing applies for the negative correlations. There's our perfect negative correlation, a value of R that's -1. There's our strong negative, a value of R that is less than 0.7, or between -0.7 and -1. And there's our weak negative correlation. And obviously the no correlation, you can still have a very, very weak negative correlation between -0.4 and 0, but it's that weak. So, well, really there is no real link between the two variables. So this slide here is the key one you need to know about when it comes to interpreting the pmcc and what it means in the context of the particular data set that you're looking at. And with all interpretation questions, it's always important that you link your statement, whatever you're saying about that data set, you link it back to the context. So in this particular example, I'll be saying, okay, we've got R is 0.953, so there is a strong positive correlation between the temperature at which the experiment was done and the amount of chemical yield that it gives off. Okay, so moving on, the other thing that we're going to get off our calculator is the coefficients for the linear equation of your regression line. So essentially the straight line that is your line of best fit. So here's our experiment again. And we've got the line, it's a straight line, the line of best fit that goes on the graph in the form y equals ax plus b. And you will find that when you enter all that in from your calculator will give you values for this particular experiment that look like that. So what we've got here is, there's our value of R, and there's our values of the coefficients a and b. So what that means is the equation of our regression line is that. So we've got minus 0.576 plus 0.24x. And again, you're going to get asked to interpret that and potentially criticize that. And you're going to see in a second that it might be already you've spotted where there's a particular issue going on within all of that. So let's just have a little look at what those coefficients mean. Let's start off with the gradients. The gradient of the line is always about how much one thing increases compared to a 1 unit increase in the other one. So in this particular context, and again it's about making it contextual, we're saying the yield is going to increase by 0.024 grams for each 1 degree increase in the temperature. So that's the gradient bit sorted. What's going on with that bit, which is the y-intercept? Well, what we're saying here is at 0 degrees, the yield is minus 0.476 grams. Now that makes absolutely no sense at all, because what it's saying is at 0 degrees, we're producing negative yield, which just can't possibly happen. So you'd be expected to realise that that doesn't make a lot of sense. So what's going on there is that although there's nothing wrong with this value, this is the correct value for this that gives us the equation of the line, but what we've got is an issue with extrapolation. So what we're saying is that all of these reactions were happening at temperatures over 100 degrees, so it is not realistic to extrapolate this straight line outside our range of values. So therefore, for values below 110, it might be that this equation here is not relevant anymore, because it might be you get to a point where you don't get any yield below certain temperatures, so the equation doesn't hold. Again, which means it doesn't mean that this is an incorrect figure, it just means we can't extrapolate beyond the range of values. And so a lot of what you're going to be getting is going to be the stuff that you're seeing down here on this right hand side here, saying, okay, get the numbers off the calculator and then interpret the figures that you've got in the context of the data set that you're looking at.